at an optimal solution. Okay. As choices are made, sub-problems of the same form arise. Okay. So if the sub-problems of the same type are not possible, and like a divide and conquer, even dynamic programming cannot be applied. So what it means is you are finding the shortest path from A to Z. Okay. Now what I will do, I will break them into small problems. A to J. Okay. K to X. Something like this. So, but these sub problems are also of the same nature. You want to find the shortest between A to J. Okay. So if it changes, your path changes, your objective changes, then they are of not same nature as that of a original problem. Therefore, you cannot apply the dynamic programming, just like divide and conquer. So in a nutshell, the sub-problem should be of the identical nature to the parent problem or original problem. Okay. And DP dynamic programming is effective when given problem may arise from more than one partial set of choices. Okay. And the key technique is to store the solution to each sub-problem in, in case it should appear. That means if that answer is to be used, then only it will save. Otherwise, that won't be computed at all. That is another beauty of dynamic programming. And in divide and conquer, what happens is the sub problems are independent. Though they are of same nature of original problem, they are independent. Okay. But in dynamic programming, okay, sub problems are not independent. Okay. So, uh, therefore, there may be something like a overlapping. Okay. So therefore, dynamic programming does more work in that sense. Okay. And it always solves the problem, every sub problem just once and saves it in the table. Okay. Unlike divide and conquer may do it twice. Backtracking solves it multiple times. Okay. As the tree explores. So that also is going to have an impact on this. And then applications. It has got a variety of applications: bioinformatics, control theory, information theory, operation research, theory, graphics, AI systems level. There are plenty. Okay. And some famous dynamic programming algorithms which are even used today is Viterbi for hidden Markov models, Unix different for comparing two files. There also dynamic programming approach is used. Smith and Waterman for a sequence alignment, you know, there we use it. Bellman fold for shortest path routing algorithms in networks. Okay. And CYK algorithm, Koch, Kasumi, and Younger for parsing the context-free grammars. So there also dynamic programming is used. And the basic, okay, you are noting something. Okay. So basically, it works on the principle of optimality. The dynamic programming working principle is it works on the principle of optimality. And El restaurante. So what I was saying is the working principle of dynamic programming is it works on the principle of optimality. It works on the principle of optimality. So as I was telling that it breaks the given problem into sub-problems and each sub-problem is solved by the same approach recursively. Okay, so that means that while solving it, again, we are not having a different approach for each of the sub-problems. And solution to a problem using a dynamic programming can be found out either by backward reasoning or by forward reasoning. Okay, so that means I can start from bottom to top or I can start from top to bottom. Okay. Now, what is this optimality principle says is, the optimality principle says the sequence of decisions D1, D2, so on up to D and is said to be optimal. The sequence of decisions D1, D2, Dn, the sequence of decisions. These decisions are emerging out of the sub-problems S1 to Sn. Okay, so then these are said to be, this sequence is said to be optimal if k last k decisions, that means k line between 1 to 10. Okay, last k decisions are optimal. Okay, the optimality principle states that the sequence of decisions D1 to Dn is optimal if and only if the last k decisions are optimal. Okay, so that means that when you go to the second step, you find some decision. That decision is going to be optimal provided the first decision is optimal. So that means that in that sequence, that is why it is phase wise. Okay. And these decisions are to be applied while solving the problem. So that is a basic principle of this, right? Now, is that okay? So what I am discussing is basically model of dynamic programming first. Okay, so what is it? Okay, and then why it is essential? Okay, now the basic principle, working principle is it is going to break the problem into sub problems, right? And for each sub problem, we make a decision, and the decision or the optimality is ensured by the principle of optimality, which states that a sequence of decisions D1 to Dn are optimal if kth last decisions are also optimal. So, okay. Right? Okay. So the steps is characterize the structure of a optimal solution. That means what I am looking at. A problem solving using dynamic programming. And which type of problems can be solved using a dynamic programming? The two main properties of a problem suggest that the given problem can be solved using dynamic programming, which are having overlapping subproblems and optimal substructure. We should have overlapping subproblems and optimal substructure. That means that there has to be a kind of overlapping from the current sequence to next. Okay. And each structure has to have a optimal solution for that. Okay. Supposing that that particular structure doesn't have a optimal solution at all, so then you cannot apply. So what are those two things which the problems which have got overlapping substructure and optimal substructure, overlapping subproblems and optimal substructures. Now, why we are talking about overlapping subproblems is it means that somewhere, in the uh, uh, later stage, I may be requiring the solution which is found previously. Okay. So therefore, this overlapping subproblems. And in that case, dynamic programming is the only method which, gives the better and effective solution. Okay. So some points on overlapping subproblems. So the base common thing in both dynamic programming and the divide and conquer is the divide and conquer also goes for combining the solutions for subproblems. So does dynamic programming also. And it is mainly used where the solutions of one subproblem is needed repeatedly. Okay, so that means because of that, you need not have to recompute. Because of that, you need not have to recompute each or that particular substructure over and again. Okay. Now, suppose that a problem doesn't require to use the recompute over and again the same thing. So in that case, I need not have to worry about dynamic programming. Okay. And the computed solutions are effectively stored in a table. So therefore, anytime I can go back and refer to the solutions or answer the findings rather than redoing the same thing again. Okay, so therefore it avoids recomputation, and hence this technique is needed where overlapping subproblems do exist. Okay, for example, binary search does not have overlapping subproblems. Okay, it doesn't have overlapping, left, right, हो गया binary search का. So therefore, their dynamic programming is of no use. We go for divide and conquer. Okay. So now, if you look at a recursive Fibonacci numbers, wherein overlapping sub problems are there, so there divide and conquer won't help. There the dynamic programming will come in picture. So given a scenario to you, general description of a problem, I should be in a position to find which method is relevant and why. So while finding that, what I should understand is when it can be applied. So that part I should remember. Okay. Yes. Then optimal, moving on to optimal substructure. You can just read it. Right. So as I was mentioning earlier also, a shortest path from say U to V. And if X is a path, a city or a node in between, that means the total shortest path will have be U to X and X to V. Okay. And standard all pair shortest path algorithms like a Floyd-Warshall and Bellman and Ford are typical examples of dynamic programming. So, so just to reiterate the same thing, the first step is characterize the structure of optimal solution. Second step is recursively define the value of an optimal solution. Then the third step is compute the value of an optimal solution, typically in a bottom-up fashion, but that is not a thumb rule. Okay. And construct an optimal solution from the computed information. Right. So these are four basic steps which are used when we want to design a dynamic programming. Okay. So I have written that in a different color, characterize. So these are basic, things which we need to identify. See, actually, when you are going to design a new algorithm itself, so these things I should be in a position to define on myself. And then I will be able to write a good algorithm using a dynamic programming. So with this basic, we'll move on. Where is it? Any questions so far? Any questions?
Yes, sir.
No. I'm now going to take one important example on dynamic programming. So let's take 5 minutes break. 5 minute break. And board वरचा दिसतोय का लिहिलेला? झूम करून बघावं लागतोय. शिवांगी
हा सर. नाही सर, क्लिअर दिसत नाहीये, पण झूम केल्यावर दिसते थोडंफार.
बर बर ठीक आहे. आता काही नाही करू शकत त्याला मी. पण नाही आणली. We'll just check if don't have a slide for that. Anyway. आणि तुम्ही बाकी लोक का नाही आलाय कॉलेजला? रोहित, प्रतीक्षा, अवंतिका, सौरभ. कॉलेज रोहित वर्किंग आहे. बाकी सगळे यायला पाहिजे ना. म्हणजे आता एकटांसाठी आपण थांबत सुटलो की मग नाही जमणार, हे काही होणारच नाही. जस्ट 5 minutes. Okay, anyway, I have one thing here which I'm trying to see. So we'll wait for 5 minutes and start with one example of application of dynamic programming or a use of dynamic programming, because we have left out with very less time, you know, and three concrete units. That's going to be very much difficult for you also. So therefore, I make sure that you don't miss these lectures sessions. It doesn't mean that you can't prepare on yourself, but it will take a hell lot of time. And let's say for first test or this INSEM, if we would not have discussed on a questions, okay, or if I would not have been a bit of leniency, the question paper would have been totally different. And for these, the next 3 units, there is no other option, but you have to work on that. Okay. So therefore, make sure that you don't miss out the classes. And if you miss, you have to read it and come. Okay. Because everybody will start pushing for their subjects. Okay. आणि मग त्याच्यामध्ये सॅटर्डे संडे सुट्टी, बरोबर, इलेक्शनचं एक सुट्टी, तर म्हणजे हा सगळं काउंट करत ना हार्डली वी गेट 30-35 days मॅक्स. त्याच्यामध्ये 3 युनिट संपवायचे आहेत प्रत्येकाला. ओके, एनिवे विल मीट आफ्टर 5 minutes जस्ट. Anthony. दिसत नाही म्हटल्यावर पण we just see the different problem. Okay. So is this visible screen?
Yes, sir.
And आवाज येतोय?
Yes, sir.
Okay.
हॅलो सर. सर व्हिडिओचा आवाज नाही येते.
Sorry.
व्हिडिओ मध्ये आवाज नाही येते सर.
नाही. वेगळ्या पद्धतीने शेअर करावं लागेल. विंडो ना. आता येतोय?
नो सर.
Include sound, correct.
Coefficients
Now-
and then we
Yes, sir.
will
Audible.
see how this problem can be or finding the binomial coefficients can be done effectively in using a dynamic programming method. So we all know that the binomial coefficients play a very vital role, right from finding roots in high power equations. When power of the equation is too large, it's going to be much more simpler using a binomial coefficient theorem and working on that. And on the similar note, if you look at applications involving statistics and a probabilistic analysis, so there also binomial coefficients play an important role. And significantly, we find the applications of binomial coefficient theorem in forecasting cost estimation in engineering problems, and so on and so forth. So therefore, it's an important topic which we have to look at it carefully, and effectively we are looking at finding the solution through a system, computer, and obviously a dynamic programming approach proves to be an effective one. So very quickly we will have a look at this notion. Okay, so here we are. So basically, a binomial coefficient with respect to mathematics is an algebraic expression of the sum or a difference of two terms. Okay, so it is thus a two-term polynomial, right? So that's the background we will start with. So it's an algebraic equation with two terms, either a sum or a difference of the two terms, and hence it is a two-term polynomial. And it's basically of the form a x raised to m plus b x raised to n, or it can be x or it can be y also, or I can write it as say a x raised to m for a generality purpose. It can be b y raised to n. So this is a general form because there are two terms and they involve summation of that, but you can just look at these terms. So we'll come back to this degree and how does it happen. For example, you can look at say this 2x square plus 7y square, x plus y, xy square plus xy. Say these are all examples of binomials, right? And binomial coefficient allow us to calculate the number of ways to select a small number of items from a large group. Essentially, they permit us to select or calculate number of ways in which we can select a smaller number of items from the larger group. Okay, and essentially the binomial coefficients are positive integers and which happen to be the coefficients of in the binomial theorem. So I will not go into detail about the binomial theorem at this moment. So you might have studied earlier, and if you are not, you go to the video and refer to binomial theorem again. So let's say we have a one equation. Is it having a binomial form? Yes, x plus y whole square. So it turns out to be what? X square plus 2xy plus y square. So this has got a all the components in two terms. So it can be easily computed, isn't it? So we can find the roots very easily. Now, what is going to happen if my equation is say x plus y raised to 7, isn't it? So it is going to be first of all a tedious as well as it involves a lengthier computations, right? And therefore, a theorem of a binomial coefficient help us to solve such a bigger binomial expressions. So that is what is background. And let's continue with a couple of background here before we go to dynamic programming approach on that. A binomial equation is of the form x plus y raised to n, which can be written as x plus y raised to n, that is equal to nc0 x raised to n y raised to 0, nc1, correct, x raised to n minus 1 y raised to n plus nc2 x raised to n minus 2 y square plus so on up to ncn x raised to 0 y raised to n. So this is how we can expand binomial equation of the form x plus y raised to n. Okay, and here nc0, nc1, nc2, ncn, they're all binomial coefficients. Okay, and we can compute a binomial coefficients using a standard formula C of nk, right? Is n factorial upon k factorial upon n minus k factorial. So you got a large number n, you want to select a smaller subset k, n factorial upon n minus k factorial into k factorial. Okay, so let's look at quickly one quick example. X plus 5 raised to y, 5, x plus y raised to 5, you can represent as what? N is here 5, n is 5. So 5c0 x raised to 5y0, 5c1 x raised to 4y1, 5c2 x raised to 3y2, y square. You can just note that c value turns out here and x value keeps on reducing the power and y power keeps on increasing. When we reach 5c5, x raised to 0, y raised to 5, that means everything is over. Effectively, we have made check for all combinations. All right. So now for the values of k is equal to 0 or when n is equal to k, c of nk will become 1. Okay. So this is one note we should remember for k is 0 because you are not picking any up and you are picking everything. Okay. So therefore c of nk will be only 1. Okay. So with this one, we can substitute and find out from this equation. We can find out for each of this 5c0, 5c1, 5c2, 5c3. Okay. So here 5c0 means k value is 0. So therefore it will directly turn out to be 1. So the first term has yielded you here 1 into x raised to 5 y raised to 0. Now 5c1 is equal to 5 factorial upon 5 minus 1, that is 4 factorial, into k is how much? K is here 5c1, 1. Okay, 1 factorial. So that turns out to be 5x4 plus y raised to 1. And continuing in this fashion, you are just to substitute. We are finding this value using the equation out here. Okay, 10x cube plus y square plus 10x square y cube plus 5x1 y4 plus 1x raised to 0 y5. So we have got all the values for nck in this for this equation. Okay, for this polynomial you can say. Okay, now look at the coefficient sequence. Okay, so I will just put all these ink marks up. Okay, so now if you look at the coefficient terms out here, in the first one coefficient is 1, second 5, here it is 10, third one is 10, 5, 1. So I have written it here. So 1, 5, 10, 10, 5, 1. So this sequence you can just see on either side 1, 5, 10, 10, 5, 1. Okay, so this is because of the property of symmetry in the combination NCR is equal to NCN minus R. So because of that symmetry, you are finding this one. Okay, and this pattern can be visualized also by what we very well known thing is a Pascal triangle, right? And you might have heard about this Pascal triangle. Okay, so we can also visualize this one. And now let's move on with the next one. Let us illustrate.
Any questions here? If you have.
No, sir.
No, sir.
5, 1.
Yeah. Yeah. Correct. So this is how we formulate a Pascal triangle. So now what is happening is 1, 5, 10, 10, 5, 1. That's how the coefficients turn out to be. Okay. And one important thing is here, the binomial coefficients help us in different applications. Okay. We are not trying to just find a binomial coefficient using dynamic programming. Now, as you can just see that there are a lot of computations here involved in doing all these things. But if I use a dynamic programming approach, finding it will become easier. Okay.
Okay. So this is because what we computing how nck is equal to n factorial upon k factorial into n minus k factorial. Let us represent each time how the breaking happens in a form of a tree structure.
And now what I'm trying to explain here is how many times when we're talking about 4C3 calculation, we are doing using the formula and substituting it. But how internally it does, the system has to do it. Okay, and how it is done, that we are trying to see. And that's why we are trying to explore that why the dynamic programming will come in picture.
Sure. So initially you are trying to find C of K3, that is for C3, isn't it? We have written like this. So it breaks down to C32 and C33. According to that formula, you can just refer back. Then further, C32 will go to C21 and C22. C33, 3 minus 1 is 2, and this is 2. And then here it is 3 minus, and this will remain as it is. So like that, C23. So you will get onto this. The next level will become C10, C11, C11, C12, C11, C12.
Are you getting how these are coming? See, C43 आहे. C43 वरनं C32 कसा आला? N is 4 and K is 3. N minus 1 next term ला गेला. Next term ला गेल्यावर N minus 1 झाला आणि K minus 1 पकडला. So one possibility is C32. Okay. The other possibility is N is minus 1 and keep K as it is. That's how we do it. Why nahi? म्हणजे see, effectively what we are doing is once we are reducing one, both N and K. In another one, you gradually go on reducing N. Okay, keeping K as it is. So therefore what we got here is C32 and C33. So if I compute these two, I can find the value of C43. See, C of NK, NCK is equal to what? K factorial upon K factorial into N minus K factorial. So if I have found 3, 2 and 3, 3, I can find the value of 4, 3 because already it is there, only one step ahead. Okay. Now on the similar note, this will get, if you look at here, N पण reduce झाला, K पण reduce झाला. Here N, K is same, N is reduced. On the right hand side, what we are doing is N is reduced, K is keeping same. On the left hand side of each branch, each node, we are reducing both. So because एक काय होतोय, आम्ही काय म्हटलो, N आणि K सेम असला तर 1च येणार व्हॅल्यू, किंवा K 0 असलं तरी 1 येणार. So therefore the only alternative is reduce N as well as K. Okay, since they are not equal, or only reduce N. का म्हणजे तुम्ही एक बाजूला in the left side you have chosen one item, so left out item is only one less than the original one. That's all.
Okay, and here like this. Now you can notice that these terms here, K value has become greater than N. N is 1, K is 2. It's like this here also. So that means that they're not, when K is greater than N, C of NK will become 0. So effectively what we are getting here is for K is greater than N, C of NK is 0. And for N is equal to 1 and K is equal to 1, C of NK is equal to 1. And that's what we had used. So this will become 1, 1, 1, 0, 1, 0, 0, 0. So we are here up to show something different. Okay. So what is that you can observe from here? What you can observe? If you look at this, there is a keen observation you can make out. So at each level, some computation is being done. Okay, that is what is being highlighted out here. Okay, so if you look here, there are some common computations which are coming up at some level. See here, C22 and C22. So while computing C of 32, you have to have this. When you are computing C33, you have to have C22. Okay. Similarly, when you go to the next level, these are common. C11, C11, C11 out here. Then these are C12, C12, C12. So that means that the same computations are being done repeatedly over and again. So that means that this in this square bracketed ones indicating that there are duplicates or multiple computations. So what we can do is, instead of that, if I memorize this answer, okay, if I memorize this answer, while when you memorize this, when you are solving this sub problem, what is the main problem? This is a main problem. This is a sub problem. You have broken it, okay, and this you have already found. I will memorize. Now when you are solving this particular, sub problem, this requires the value of C11, which is already here. I'm just giving an example, okay, because I have taken a simple formation of a tree so that you will understand the notion. But when this n value is k values are much different, the tree will be growing on and multiple intermediate computations will arrive. So I can memorize it. And since I have memorized the answer for what? It is an overlapping subsequence, isn't it? So this sequence is overlapping when you are solving the sub problem S1 and say sub problem S2, isn't it? So I am remembering
Are you
that.
getting it? Right. Yes, Agla, you don't look at C43 and all. You assume that P is the problem, S1, S2, S3, they are the sub problems. Now, these which we have circled here, like these are the overlapping sequence. Okay, so that is why the dynamic programming will come in
Memorizing
picture.
that sub problems. Why we are remembering? You don't want to recompute here. You have to directly use it. So this is what we are coming as an observation. It has got multiple computations and duplications, all right, and we can therefore memorize the results of overlapping subproblems and avoid recomputations. And when you see overlapping subproblems and memorization, one algorithmic strategy strongly support, that is dynamic programming. And therefore we are now up to solving a binomial coefficient or binomial formula in for using a dynamic programming. So I guess you have followed this. This is a P background, and now we will formally see a problem formulation for binomial formula, right? So I had already discussed this. X plus y raised to n can be written as nc0 x raised to n, nc1 x raised to n minus 1, and so on up to ncn x raised to 0 y raised to n. And we had also seen nc0, nc1, and so on. They're all binomial coefficients, and binomial coefficients can be determined using this formula. Now, what we do is, based on this formula and the example which we took earlier, x plus y raised to 5, okay, based on that we can write a recurrence relation. Okay, so C of nk, it will be equal to what? 1 when the value of k is 0, when the value of k is 0, or when n is equal to k. All right, correct. This is what we had seen. Then otherwise, if you look at the tree, right, what was happening in the one phase, n minus 1 was happening, k minus 1 in one group, and it was summed up with what? N minus 1 and k, isn't it? So, and these were giving you the intermediate nodes. In the previous slide, we had seen that. So therefore, for n greater than k greater than 0, what will happen? It will become C of n minus 1, k minus 1, and C of n minus 1, k. Okay. So this is the recurrence relation for binomial formula. Okay. Now, what we'll try to do is, we will use a dynamic programming to solve this. So when we are solving it, we'll construct n by n is here. So n by n matrix, and fill up either upper triangular or a lower triangular, the way in which you organize your structure. Based on that, we can do that, and we can avoid the repetitive computations. So let us see that.
Any questions here? Any questions? आपण काय करतोय, binomial coefficients find out करतो. Why? Because when you have got a polynomial of a higher degree, binomial म्हणजे काय? 2. Polynomial म्हणजे many. So variables we had only 2 here. Okay. So in that case, if it is a simple one, x plus y raised to y square or a cube, doing it is simple. Okay, but however, when it goes on increasing, the power goes on increasing, expanding the terms will also become difficult. Okay, or time consuming. And therefore, even if you write a program also, that is going to change for each sequence of a power. But if you write it once for a dynamic programming, I need not have to modify anything except for giving the input ranges. Okay. Any questions?
No, sir.
Okay.
Find the binomial coefficients of x plus 5y raised to 5 using dynamic programming. This already we have seen without.
What we had done earlier, we had used this explicitly the formula to calculate it. That we had used NC0, x plus y raised to 5 find out करायला. Nचा value काय होता 5. 5C0 x raised to 5. Explicitly we found out. Now how we can do it using a
dynamic programming, explicitly computing the values and substituting. So let us see whether we get up in the same spot or not. So first let us consider n by n matrix. Okay, so this is my 0th first column, second column, 0th column, first column, second. This is third column, fourth column, and fifth column. Okay, so one extra we will be taking n plus 1. So similarly, so this is 0, 1, 2, 3, 4, and 5. The rest of the elements of this n by n, okay, are removed because they are not going to be computed at all. Now, as I
was saying that I can use a lower triangular matrix or a upper triangular matrix. So this is because n was 5, right? So though I am starting it from 0 index, but it is n plus 1 by n plus 1 matrix. But however, within that you can just see that the upper cells are removed. Okay, so we will be talking at the lowest row, all 5 columns are existing. Fourth la, एक column diminish होतो. So every time it goes on reducing. When it comes to the 0, there is only 1 column left. Okay. Right.
As per, so this will be our k and this will be our n. Okay, n is this side and k is this. So when k is equal to 0, C of nk is.
You listen to this, no, because it is very simple, very simple. Okay. And very much effective while you solve the problems, right? Okay.
All one. They're all one, irrespective of the value of n, isn't?
See, when k is 0, right? Whatever may be n, the value is going to be 1. So therefore, the first column entries are all 1s.
Right. That is what we had defined even in the recurrence relation. When k is equal to 0, then whatever may be the value of n, they will all become 1. So you have filled what? When k is equal to 0. So the first thing what we have done is for k is equal to 0, we have put the matrix entries as 1s. No problem at all. Okay. Now for the second thing is the base conditions. For n is equal to k, for n is equal to k also, we are going to have the value as what? 1 only. For n is equal to 1, sorry, n is equal to k, the values are going to be 1 itself. So that means all the diagonal elements, that means 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, all are going to be 1s. So 0, 0 is already made as 1, 1 first, n is 1, k is 1, that is also 1. When it is 2, 2, you will make it as 2, sorry, this is also 1, this is also 1, this is also 1, and this is also 1. Now,
Right. Understood? So first K0 asthana, that column will become all ones. Then all diagonal will become 1 because n is equal to k. N value ikkade, k ikkade. Right? Okay.
Now, a very simple thing to calculate other elements. Okay. Now, what we'll do is to calculate, compute the other elements, find the sum of previous two cells. What is that? Find sum of previous two cells. Okay. So while you want to compute the other elements, let us take one example quick. C21, C21, C21. That
Cell number, second row and first column. Right? Okay.
is here. This cell is here. Better use a different pen so that you can make out. Yes. So this cell, right? So we are talking about this cell here. You can just see that C21 is equal to sum of the previous two cells. Sum of the previous two cells is cell 10 plus cell 11. Cell 10 plus cell 11. Even if you substitute in the formula, you will be getting this only. So directly we can use this computed value and add it here. So this will become 2 and this is 1. Okay, right. So now, is that okay? Right. Now, what will happen with cell 31? Cell 31 will be what?
What will get? Cell 31. हे कॉम्प्युट करतोय. हा, याचा व्हॅल्यू काय येणार? सम ऑफ द प्रिव्हियस टू. राईट? हे बाकी लोक आहेत का?
Yes, sir.
हा, शिवांगी झोप झाली का? झोपलेत ते खरंच.
Previous to this you are
Sorry? नाही, इथे तर डायरेक्टच आपण मेथडला चालू ना. आपण ट्री मध्ये फॉर्म्युला वापरले. हा, इथं फॉर्म्युलाची गरजच नाहीये. So we are just using this funda and directly substituting it. Okay.
computing. So previous to this plus this plus this. So that will become 1 plus 2. That will be 3. And when you are computing C32, when you are computing
Previous
C32,
to, right?
what will happen now? C32. Yes, quickly. C32 will be equal to C21 plus C22. Am I right? Okay. So this will also become 2 plus 1, that is equal to 3. Am I correct? Now going to 4, 1, cell 4. So 4. So that we have 5, 10. So 4. So that.
So you can just verify this when we are going into 4, 1, previous to 1 plus 3 is 4. When you go here, 3 plus 3 is 6. When you go here, 3 plus 1 is 4, right? So when we are going next now, 1 plus 4 will become 5 here. 6 plus 4 will be 10. 6 plus 4 will be 10. 4 plus 1 will be 5. So I'll just forward this.
You have got 1 by cube. Just will rub this, right? Is to 4. Look at this one. What you have got? 1, 5, 10, 10, 5 and 1. So these were the answers we had got. The value for x plus 5, x plus y raised to 5 as the coefficients. So this will be 1 x raised to 5 y raised to 0 plus 5 x raised to 4 y raised to 1 plus 10 x raised to 3 y square plus 10. I'm using these coefficients. Okay. 10 x4 y raised to sorry, x square and y raised to x square and y cube. Just will rub this right. Okay, so 10x square y cube plus 5x y raised to 4 plus 1 x raised to 0 y raised to 5. So the same answer we had got while we explicitly calculated. Okay, so in a more power terms you can use this dynamic, isn't it? It is simple. What is that we did? For k is equal to 0, the entire column value is 1. Diagonal elements are also 1 because when n is equal to k. Then while computing for the next cell from a top down, it is a sum of previous two elements. Okay, so that is much simpler and a easy way of computing the binomial coefficients using dynamic programming. And this we have seen, so that's a very simple thing. What we is equal to n, so that's a very simple thing what we have done. And if you want to have a look at the code, again, it's going to be pretty simple. Binomial coefficients will be passing on the values of n and k. And if k is greater than n, then what we are doing, you are returning 0. If k is greater than n, you will return 0. And if k is equal to n, or if k is equal to 0, if k is equal to n and k is equal to 0, then you are returning the value of 1. Just convert that recurrence relation into a formula and write the code. That's all. Otherwise, you return, what you will return? You can call this binomial coefficient recursively n minus 1, comma k minus 1 plus binomial. We are calling that function binomial coefficient n minus 1 and k. Correct? So that's all. So that's the end of a simple code if you're trying to write a function using a dynamic programming. I think you have followed it. There's nothing to be worried, and you can have a look at it and solve more examples.
Any questions?
No,
Any
sir,
question?
clear.
Clear. Okay, so basically आपण काय केलं की we just found out the binomial coefficients. Okay, so now binomial coefficient कुठं कुठं यूज होतोय. ओके, सो तिथं आपल्याला एक्सपांड करायला मल्टिप्लिकेशन, आता x प्लस वाय स्क्वेअर असलं तर पटकन केलं, x प्लस वाय रेस टू 7 असताना अवघड होतंय. सो तो ह्याच्यामध्ये काय की एक सिंपल थंब रूल लक्षात ठेवला की आपल्याला पूर्ण सिंपल येऊन जातोय. आणि आता जे काही पास्कल ट्रायंगल जो होता, दॅट ऑल्सो वर्क्स ऑन द सेम प्रिन्सिपल and which is predominantly used for many of the applications in theoretical as well as research applications of physics. Okay, right. So later, so you remember those who are present, absent, I don't know, but you first know what is dynamic programming, what are the characteristics of dynamic programming, right? Then we did discuss about steps involved in it. Dynamic programming works on the principle of optimality. And the first example to solve binomial coefficients, finding a binomial coefficients using dynamic programming. Now, what I will suggest you is you search for the journal papers which talk about a real-time applications of binomial coefficients, use of binomial coefficients, and you take any one example of your choice and elaborate on the same. Correct? The last thing which we saw was the code for finding the binomial coefficients, right? So the last line in that, you were recursively calling that previous cell, you know. That's how I explained within the example addition of previous cell. So recursively, whenever you call, it goes on filling it. It remembers, it pushes the content onto a stack so that effectively the table itself is getting created out there. Okay. Now, if you want to try, you just display that, you know, when you go for that, you are returning the value of 1, 0 and sum. There you just display nk value and what is the return value. So you will come to know that, you know, okay, these coefficients are coming out in that manner. Any questions? Ruchita, Saurabh,
No,
Shivangi?
sir.
No. Okay. So actually, if you would have been in a class, I would have taken the other example also, in the sense, other type of an example, because this involves, you know, many things in this particular chapter. Like first part is a dynamic programming, second is a linear programming. Okay. And now we have done one part of it. Then there are two more examples, example of use of a dynamic programming. And then comes the important thing is analyzing those algorithms, right? I have to analyze that algorithm and come up with again. That won't go out. Okay. Writing a recurrence and coming out with a notation of a theta or omega or O. So the end that has to be there. Okay. Now, as a variation to this, you may be given a scenario. Okay, not directly giving a binomial coefficient or trying to give a direct problem statement as such like this. And you may be asked to solve it. Okay, so I should be in a position to find from the problem, yes, there are sub problems or not. Substructure hai kya, overlapping hai kya. So that way I should be in a position to find out and then find a final solution. Okay. So I think I will halt here, and tomorrow you do come for the class. Those who are not here, okay. Just sir, इस तारीख का है आपला? अच्छा. Alright. Fine. Okay, I have done with my things. If you have questions, you can ask. And maybe for instant papers, they will show you answer sheets. Okay. So I don't know. They have decided the date of 9th. Okay. So maybe you can view the answers. Right. Okay. Any questions? 9?
No,
No,
sir.
sir.
Okay. So we'll stop here and tomorrow we'll start with the new application of dynamic programming. Okay. Yes.
Okay.
Yeah. You can leave now.